Good afternoon, ladies and gentlemen. Happy Friday. Today is April 23rd. After today, there are only 4 full school weeks left, which is exciting news. Then today's Friday, right? 2 good things to look forward to. So let's go ahead and get started. We have a few things to get through today. So first up is a bell ringer on magnetism. Iron filings and a bar magnet were placed on a sheet of paper. The following diagram shows the pattern made on the paper. So look at the two magnets and their interaction. At which location is the magnetic field the strongest? So I'm going to refresh so that I can see some of your responses. And it looks like most of you guys chose option D, which is area 4, and that would in fact be correct. So I wasn't able to demo this for you guys, but we did this in class. We took a bar magnet and we sprinkled iron filings on top of a paper and put it on top of the bar magnet, and we were able to actually see this happen in real time. Now, if you have 2 bar magnets, it's a little different. So with 1 bar magnet, remember the strongest magnetic field comes out of each end of the magnet. But if you had 2 magnets together, you would in fact observe the strongest magnetic field occurring between them where the attractive ends are. So the north and south. So good job on that one. Little preview about what we're doing today. So we are going to watch a video on the difference between batteries. And in class, we've been talking about the difference between dry cell batteries and what we call wet cell batteries. And I'm going to go over that with you guys in just a moment. But we're going to move through a video today. And then where it says virtual students only, there is a short Nearpod. Now there's a student pace link, but I'm also going to do an in-class version for those of you that are present with me in the WebEx. And then we will break and you guys will do an independent activity introducing circuits. So let me change my settings and you guys get ready. And I'm going to show you a little bit of a kind of introduction video on how batteries work and the differences between some batteries. So give me just a moment to set that up for you.
You probably know the feeling. Your phone utters its final plaintive bleep and cuts out in the middle of your call. In that moment, you may feel more like throwing your battery across the room than singing its praises. But batteries are a triumph of science. They allow smartphones and other technologies to exist without anchoring us to an infernal tangle of power cables. Yet even the best batteries will diminish daily, slowly losing capacity until they finally die. So why does this happen? And how do our batteries even store so much charge in the first place? It all started in the 1780s with 2 Italian scientists, Luigi Galvani and Alessandro Volta, and a frog. Legend has it that as Galvani was studying a frog's leg, he brushed a metal instrument up against one of its nerves, making the leg muscles jerk. Galvani called this animal electricity, believing that a type of electricity was stored in the very stuff of life. But Volta disagreed, arguing that it was the metal itself that made the leg twitch. The debate was eventually settled with Volta's groundbreaking experiment. He tested his idea with a stack of alternating layers of zinc and copper, separated by paper or cloth soaked in a saltwater solution. What happened in Volta's cell is something chemists now call oxidation and reduction. The zinc oxidizes, which means it loses electrons, which are in turn gained by the ions in the water in a process called reduction, producing hydrogen gas. Volta would have been shocked to learn that last bit. He thought the reaction was happening in the copper, rather than the solution. Nonetheless, we honor Volta's discovery today by naming our standard unit of electric potential the volt. This oxidation-reduction cycle creates a flow of electrons between 2 substances, and if you hook a light bulb or vacuum cleaner up between the 2, you'll give it power. Since the 1700s, scientists have improved on Volta's design. They've replaced the chemical solution with dry cells filled with chemical paste, but the principle is the same. A metal oxidizes, sending electrons to do some work before they are regained by a substance being reduced. But any battery has a finite supply of metal, and once most of it has oxidized, the battery dies. So rechargeable batteries give us a temporary solution to this problem by making the oxidation reduction process reversible. Electrons can flow back in the opposite direction with the application of electricity. Plugging in a charger draws the electricity from a wall outlet that drives the reaction to regenerate the metal, making more electrons available for oxidation the next time you need them. But even rechargeable batteries don't last forever. Over time, the repetition of this process causes imperfections and irregularities in the metal's surface that prevent it from oxidizing properly. The electrons are no longer available to flow through a circuit, and the battery dies. Some everyday rechargeable batteries will die after only hundreds of discharge-recharge cycles, while newer advanced batteries can survive and function for thousands. Batteries of the future may be light, thin sheets that operate on the principles of quantum physics and last for hundreds of thousands of charge cycles. But until scientists find a way to take advantage of motion to recharge your cell battery, like cars do, or fit solar panels somewhere on your device, plugging your charger into the wall, rather than expending one battery to charge another, is your best bet to forestall that fatal bleep.
All right, so hopefully you guys enjoyed that video just comparing the difference between a rechargeable battery and a disposable battery in a way. Most of us are familiar with batteries, but this also kind of helps explain why some of your laptops hold a charge for a long time and then some of yours die immediately. I know for my teacher laptop, if it's unplugged for more than probably an hour, then the battery's done. So it doesn't last very long, even though it does in fact have a rechargeable battery. So while you guys are kind of taking a minute to get settled, I'm going to go through with you and talk a little bit about the difference between what we call dry cell and wet cell batteries. So give me just a moment to change my settings. I'm going to turn my camera on. All right, so hello everyone. So a little bit on dry versus wet cell batteries. So dry cell batteries are the ones that we're used to seeing. For example, the ones that I've been using in class with you, or in class, those of you that have been coming to the virtual session, I've done a couple of demos. So a dry cell battery, I'm going to grab one for you. So here's our dry cell battery here. So this is the one we're probably most familiar with. I know this is a D size, right? A D battery. So it has 1.5 volts. And you guys are familiar with AA and AAA and things like that. So these are the batteries we're most familiar with, and these are called dry cell batteries. And so what's actually happening is if you could cut this open and look in there, there is an electrolyte paste, and that paste is what generates the electrons that flow out from one end to the other. So there's an insulator around it. There's also a little separator, and the material flows out. Over time, the electrons will eventually flow all the way out, and if it's a non-rechargeable battery, it goes dead. So this is dry cell batteries. Wet cell batteries, on the other hand, I don't have an example of that, but one of those that you can think of are the batteries in cars. So wet cell batteries actually have, well, wet liquid fluids in them. And so they're going to have different electrodes in there, and they're also going to have some type of acid mixed in with other materials. So for example, sulfuric acid surrounded by, and I'm trying to look at my note here, electrolytes. Okay. Acid surrounded by electrolytes. So I don't have a car battery to show you, but I'm sure all of you have seen a car battery. That's an example of a wet battery, which is also why if you're not careful when removing a car battery, some of that can slosh on your clothes and it'll actually burn little holes in it. So those are the two differences between batteries. Now, what we're going to do for the rest of class today is we are going to be looking at circuits. And before we start that, I'm going to share a Nearpod with you. So this Nearpod, there is a student link for students who can't be in the WebEx now, but for you guys, I'm just going to share my screen with you and go through the Nearpod that way. But the student link is available if you want to go back and replay the video. So I'm going to pause for just a moment and get that set up for you guys. So for those of you that are present right now in the WebEx, you do not have to sign in and do this Nearpod since you are present and actively participating. But if you want to access the Nearpod to go back and review whenever you're doing your assignment, you have the student link available to you. So first little pausing question, and you guys can post in the chat. What do you already know about, well, series and parallel circuits? And you can just share that with me in the chat now. Maybe you know a lot, maybe you don't know anything. All right, so I have one person. Thank you, Alyssa. So some of you know some things about series and parallel circuits. Now I'm looking at the WebEx. I have a lot more than one person in here. So if you're active, you guys need to be participating. All right, thank you, Mark. So even if you know a lot, just say, hey, I know a lot. If you don't know anything, say, I have no clue what you're talking about, Miss Littlepage. Let's keep playing the video so we can learn.
Hi, it's Mr. Anderson, and today I'm going to be talking about series and parallel circuits. These are a couple of different circuit diagrams. Remember, this stands for a battery, and each of those stand for a resistor. And so this would be a series circuit. Remember, it's a closed circuit, so there's a loop where electricity can flow the whole way around. And then we have three resistors, and so the electricity that goes through this has to go through these as well. If we look at this one, this is one battery connected to three resistors as well, but they're parallel to one another. In other words, there's three loops that electricity can take, and so we call that a parallel circuit. Now,
all right, so in a parallel circuit with three resistors, how many loops does it take? Well, what do you guys think? Some of you say C. Let's check it out. Good. All right, three of those. So what this is introducing to you guys is the difference between these circuits. Some of you are asking for the code in the Nearpod. Nobody is actually logging into this Nearpod. This is just me screen sharing and doing this as a group. If you want to do the student-paced one independently, the code is posted in the assignment. Yeah, this is just me sharing. So all you have to do for this Nearpod is post your responses in the chat and follow along on the screen.
now, the first time you look at a series in a parallel circuit when it's actually connected, there's some stuff that's not super intuitive. In other words, there's some weird stuff that takes place. But once you really understand what's going on in both a series and a parallel circuit, you'll do much better. And so today I want to show you basically a parallel and a series circuit, a few demonstrations, and I'm going to be using the circuit construction kit. This is at phet.colorado.edu, and I would encourage you to go there, play around with it. It's the best way to learn about electricity is to actually play around with it. Okay, so right here we've got two different loops. This one is so this would be a battery right here. It's a 9-volt battery. This is an ammeter, which is going to measure the amps. We've then got wires connected to a light bulb, back to a switch, and then back to the battery again. And so this would be a series circuit because electricity is going to flow in this direction through the battery and then back, through the bulb and then back again. And so when I turn it on, we can see that electrons are flowing. We've got 0.9 amps, and then it's running through a light bulb. And so these rays around the outside of the light bulb show you how much light is being given off from that.
All right, so let's see. In a series circuit with an 9-volt battery and a single light bulb, the electric current that flows is A, 0.90 amps. Good. I see a lot of you posting. Thank you. So you guys are obviously following along. And as mentioned, this website, the FET website, is the one we've used all school year long for our different virtual labs. So we might actually visit this next week. So this is kind of a nice preparation for that. So let's continue and see what the difference is between the two circuits.
And so the first thing I'd like to do, let me turn that off for just a second, so let me open that circuit for a second, is kind of get a sense for how much electricity is coming out, or how much current is flowing through there, and how much light are we getting off of that. And now I'm going to add another light bulb, and I'm going to put it in series. So let me add another light bulb here, and I have to break this, split the junction, and let me connect to both sides of that. And let me move it down so it looks a little better. Okay, so now we've got two light bulbs. We've got the same battery. You kind of remember how much light we were getting at it before, and you remember the speed. And so let's turn this one on now. Okay, so in a series circuit, what we have now is those two bulbs are not as bright. And the reason why, and if you remember how much speed we were getting, or how much current we were getting, remember it was 0.9 amps. And so in a series circuit, if we add more resistance, we're going to decrease the amount of current. And as a result, we're going to have dimmer light bulbs. And so
All right, so in a series circuit, adding more resistance will do what to the amount of current? C, decrease. Good job, you guys. So obviously when he added that light bulb, well, it changed the amount of current. Not only are the electrons moving more slowly, but the bulbs are much, much, much dimmer. And that's now because the electrons have to move through both of those, right? They're going to come down, move through the first bulb, and then move through the second bulb before they can make their way back around.
And so the current is going to be the same through every component in a series circuit. And so the other thing about a series circuit is, let me try, let me remove this. So let me split the junction. Okay, so when I split the junction there, I cut that wire, and so it wasn't connected anymore, and so both bulbs went out. And so the two things that you should learn, number one, is that in a series circuit, all of them have to be working for current to flow. And the second thing is that they all have the same amount of current. Volts is another thing, and so let's add a voltmeter as well. So if we add a voltmeter, this is a 9-volt battery. If we look on either side of the light bulb, we'll find that the volts are 9 volts. If I move this lead over here, this electrode over here, we find that it's 4.5 volts. And then if I shift both of them to this side of that light bulb, it's 4.5 as well. And so the sum of the volt, or the voltage drop between the two components in that, are going to equal the volts that we have for the whole thing. So it's 9 volts, but then each of those bulbs, it's going to be a drop of 4.5 volts. So we have 9 volts, and then we have 0 volts when we get to the other side. So let's get.
All right, in a series circuit with a 9-volt battery and 2 light bulbs, the voltage drop between the two components will be what? I don't know if that's a typo or not, right? Everybody in here says B, some say C. There's basically a drop in between them. So collectively they add up to be 9 volts, but you see a shift when you go from one to the other, right? So remember that there is a drop between them, but on the opposite side, it should go back up to the original volts.
Let's get rid of that voltmeter, and let me turn this one off. And so let's return that for a second. So get a sense of how much light we're getting from these two light bulbs, and we have 0.45 amps. And now we're going to look down here at a parallel circuit. And so a parallel circuit, there are two.
Okay, so before I hit continue, we've looked at series circuits. So everything up here, make sure you're listening closely. This is what we call a series circuit, meaning we have a power source and then we have a light bulb, another light bulb in a series in a line. So if you can visualize series circuits, think about Christmas lights. What happens if one Christmas light on your string goes out? They usually all go out, okay? That's exactly, they all go out. That's the problem with a series circuit. So that's the downside of a series circuit, which is what we have here. Now we're going to start talking about a parallel circuit, and that's going to help us understand if maybe one circuit is more beneficial of the other. So let's listen closely to parallel circuits.
Parallel pathways. In other words, there's a wire that goes through this bulb and a wire that goes through this bulb. And so when I turn this on, there's a clear difference between the two. And the first time I saw this, it was totally confusing to me. In other words, these two light bulbs are as bright as that one light bulb was before, when it wasn't in series. And so the first thing that should stand out to you is that these two bulbs are as bright as that one bulb when it was before it was hooked up in series. And so another thing that's happening is that we actually have way more amps moving through this, and so you can see that the electrons are moving more quickly. And so the difference between a series circuit and a parallel circuit is that the current is actually increased. Remember when we had, let's go back and remove this and just connect it together. So remember here we had 0.9 amps for one light bulb, but here we now have 1.8 amps. In other words, the electricity is actually flowing faster. Why is that? Well, here there is the current of this thread and there's the current of this branch, and the two currents together are going to sum up to this, this current.
All right, true or false? Electricity flows faster in a series circuit. So remember, series was the very first one. So let's check. This is in fact false, okay? So the electricity does not flow faster in a series circuit, it flows faster in the parallel. So the parallel is the one we're looking at now at the bottom of the screen.
And so before, when we were saying the voltage drop in each of those sums up to the voltage of the battery, well, in a parallel circuit, those two pathways, in other words, those two currents, are going to sum up to the current of that whole, the whole branch. Another thing that happens in a parallel circuit, let's kind of remove this light bulb. And so remember when I removed a series light bulb, the whole thing went out. But in a parallel circuit, when I remove one of those light bulbs, the other one keeps moving. Now you should have seen that when I removed that light bulb, the amps dropped down to 0.9, but and electricity isn't flowing through this side. But by hooking it up this way, we've now got electricity, or a path for electricity to go. When I was a kid, I remember we had a string of light bulbs that were hooked up in series, and it was the most annoying light bulb strand that you could have for Christmas lights, because if you ever had one bulb go out on a series circuit, then the whole thing was broken all the way down. So you had to search through that string of lights until you found the one that was burned out. Now they use parallel circuits, and the reason they do that is you don't get that drop in current with each bulb, and the other thing is that you can have a break in one of the bulbs and the other ones are all going to work.
So again, this question is about series. In a series circuit, the one at the top of the screen, what happens if one bulb goes out? So think about the visual at the top of the top model. In the very top one, which is series, if one bulb goes out, they all go out, which is why newer Christmas lights are usually a little bit better. But some of them are still, some of the cheaper ones are still kind of in a series format, meaning if one goes out, well, you got to check the whole strand.
And so that's kind of an introduction to series and parallel circuits. Remember, in a series circuit, the current is going to be the same through every part of that loop. But in a parallel circuit, it's going to be the sum of the two will be the sum of the current through the whole of the circuit. And the voltage drop, if we add our voltmeter, in a parallel circuit, it's going to be the same along each thread. So remember, this would be a 9 volt on this pathway, but it's also going to be a 9 volt on this pathway. And so you're not getting anything for free with a parallel circuit. You're actually going to go through more energy using this setup than you would over here, because you're actually gathering more amps.
So what is something you're still confused about from this video? So what I wanted you to take away from this, the key difference is introducing series and parallel circuits and get you guys kind of thinking about them. So at this point, do you at least feel semi-confident in the basics of series versus parallel circuits? So remember, series has one bulb and parallel has more than one and on a separate branch, basically. Okay, good. So if you are semi-confident at this point, then I think you're good. That's the only expectation I have out of today's lesson, because we're going to continue this on Monday.
So that's parallel and that's series circuit, and I hope that's helpful.
Okay, so that's it. Kind of a short little introduction Nearpod here. And we may actually revisit this lab on Monday, but I wanted to introduce it so you guys have at least seen it. You become a little bit more familiar. So I'm going to stop sharing my screen and I'm going to minimize for just a moment and check to see if I can access your assignment. So give me just a moment. Okay, ladies and gentlemen, so on my end, Schoology is working again. If it's not working on your end or not all of the components are working, I'm still going to go over your assignment for the day so that you know what you need to do when it is up and running. So in our folder for today, I'm going to pull that back up for you. There we are. So on this virtual assignment, you're going to see a couple of things. So there is the link for the student pace Nearpod. So for those of you that want to go back or you want to review, you can either click on the link or here's the code for you to access it. This is also for students who miss class who aren't in the WebEx with us right now. Now I'm going to open up the worksheet and kind of show you guys what this is going to look like. So this is our introduction to components of circuits. This is a Google slide or Google Slides. So you're going to be typing and putting stuff in the boxes. So I'm going to go through this and explain exactly what you need to do, and then we'll break and you guys can work on it. If Schoology will let you open it. If not, you can continue working through this on Monday, but you should be able to start it today if you can access it. So remember, you can always zoom in on these. You can zoom into it or you can expand it larger. So in this worksheet, you're just identifying different components. So it says below is a diagram for a simple electric circuit. Write the names and brief information about the functions of each circuit component. So here we go. This is pretty simple. What is this right here? You guys should at least know what this is, right? A light bulb. Thank you. You have a light bulb. Scroll on down. The black line here represents your wires in the circuit. So notice this box right here points to this. So this would be the wires in the circuit. As you move along, what would you describe this object as? Switch. Thank you. You have a switch. And then lastly, you have your battery or a power source. So these are kind of your four basic components of a circuit. And you guys have seen me demo things in lab over the past few days. So you're basically going to click on your boxes, tell me what it is, and just a basic function. Then when you move on to the second sheet, again, they're going to be asking you questions about how to answer, about how circuits work, for example. So again, you have some images of circuits here, and you're going to click on the box, and this is where you will type your answers. Now, number 3 is the part I want to make sure I go over with you. And then, of course, number 4 as well. But number 3, page 3 says, circuit components are given below with their pictures. Write their names and draw their symbols in the spaces provided. I'm not going to have you draw these and submit it to me. So what you can do is you can type on here for the name. Here's a light bulb, for example. And then there are symbols that you use for this. So what you guys need to do is basically Google symbols in a circuit. And that is going to come up for you. So I'm going to pull up a tab really quickly and show you symbols in a circuit. And then look at all these things come up. So some of them are larger than others. So let's start with this one right here. And if you click on it, or some have more information than others. So this is a pretty simple one right here. And it tells you ammeter, cell refers to battery. This is a 2-celled battery, diode, a fuse, a lamp, a resistor, an open switch, a closed switch. You can look at some more. Here's another chart with all different types here. There's one right here, electrical symbols. So here's a lamp here, another switch, closed switch, open switch, a voltmeter, an ammeter. So you can find all of these just by typing them in. So I'm going to show you one of them I've already done for you. So if you scroll down, that's what this means here when I say copy and paste the symbol. So you'll have a light bulb, 1 battery, 2 batteries, open switch, closed switch, voltmeter, ammeter. And I went ahead and did this one for you as an example. So this is basically just a picture. I pulled it up on the internet, copied, and I pasted it in here and just kind of minimized it and made it smaller. So the ammeter one is done for you. This is a resistor, and then this looks pretty similar to, I'm not really, this one is a little different than what I'm used to seeing. So for this one, we'll just, we'll call this one an electromagnet since it has a coil wrapped around it. So here's a resistor here. Okay. So once you go through that, you guys can move on to the last page. And in the last page, you will be showing me a picture that you sketch. Okay. So this one says sketch or draw number 5 and 6 and send it to me in a message. So you can take a screenshot with your computer. So you can draw it in a Google slide and submit it if you want. You could sketch it on a piece of paper and send it to me. I'm very, 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 very flexible when it comes to you guys submitting stuff. Okay, so this is it. And then the last page, we'll have a couple questions. So I'm going to stop sharing my screen now, and I'm going to come back to my video so that you guys can see me. All right, so does anybody have any questions? I know we're kind of getting close to time today. It's 11:47. So if Schoology is up and working for you, then please sign in and go ahead and open this document and get started now. If you were late to join the meeting, then you need to do the student pace Nearpod because it goes through series and parallel circuits and explains the difference between those. Okay. So if you guys don't have any questions, you can break. On Monday, we're going to revisit circuits again. So you should have enough time to at least start working on this document. So I can go in and see that when it says who's accessed and who hasn't. Okay, so go ahead and open that now. If Schoology is up, start working on that. Have a great weekend, you guys. I will see you on Monday. Bye, everyone.